Unit 2, Activity 1, Introduction to Exponential Functions. In Unit 1, we studied linear functions, which models quantities that increase or decrease at constant rates. In Unit 2, we will learn about and use a different kind of model that is non-linear. This kind of function will model quantities that increase or decrease by a constant factor, such as quantity that doubles or triples. In this first activity, you will analyze this type of situation and you will learn about the form of the equation we need to model this kind of change. And learning outcomes, you will carefully document your work, including defining variables, and you will explain the meaning of constant in equations. You will also make tables and write equations to model situations. You will also use tables and equations to solve problems involving quantities that change by a constant factor, and you will demonstrate your ability to write equations to model linear and exponential data. Let's start with the warm-up problems. Simplify the following without using a calculator. The first one, 3 squared, meaning that is 3 times 3, and that is equal to 3 times 3 is 9. Next, 2 cubed, meaning 2 times 2 times 2, and we multiplied that. 2 times 2 times 2 is equal to 8. Then 2 times 5 squared, that is 2 times 5 times 5. And 5 times 5 is 25, times 2 is 50. Then 3 times 2 to the 4th, so 3 times 2 times 2 times 2 times 2. And 2 to the 4th is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 3 is, 48. E, 4 cubed times 2. So 4 times 4 times 4 over 2. 4 times 4 is 16, times 2 is, 4 times 4 is 16, times 4 is 64, divided by 2 is 32. And then 1/2 raised to the 4th power, that is like 1/2 times 1/2 times 1/2 times 1/2. 1 times 1 times 1 times 1 is 1. 2 times 2 is 4, times 2 is 8, times 2 is 16. Let's do the same thing for letter G. 2/3 cubed. So that is 2/3 times 2/3 times 2/3 is equal to 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Next, H, 2 times 5 halves squared. So that is 2 times 5 halves times 5 halves. And that is equivalent to, we can cancel the 2's here. 5 times 5 is 25. And we still have 1, 2 here. So 25 over 2. Okay. Next, match each expression on the left column with one of the expressions on the right column. 3 plus 3 plus 3 plus 3 plus 3. We know that we have 5 3's here. So 5 times 3 is 15. So that is equivalent to this. So 3 times 5. Next is 3 times 3 times 3 times 3 times 3. So meaning that is 3 to the 5th power. And then next is 5 plus 5 plus 5 plus 5. You have 4 5's and 1 3. So 4 5's and 1 3. Add 3. So 5 times 4 is 20 plus 3 is 23. So if you add all this is 23. Next is 3 times 5 times 5 times 5 times 5. So meaning that is 3 times, you have 4 5's. You're multiplying 5 4 times. So that is 3 times 5 to the 4th. Next, 4 plus 4 plus 4. So that is 3 times 4 plus 3. So this one. And the next one, 3 plus 3 plus 3 plus 3. So you are multiplying, you're adding 3 4 times. So that is 3 times 4 plus 5. This one. And the last one, 5 times 3 times 3 times 3 times 3. So you are multiplying 3 4 times 5. That is this one. Okay, so note that matches above illustrate that replace an addition with one additional value that can be written in the form of mx plus b. Also, repeated multiplication can be written in the form of a times b raised to x. So look at this. Mx plus b is linear. So it's like mx plus b, mx plus b, mx plus b, and a times bx, a times bx, a times bx, a times bx, a times bx. Okay, now let's start with our class discussion. So this is a Unit 2 Activity 1. If I were you, if you want to print out this or take, I expect you to take down notes, especially with the class discussion. Okay, number 1 problem, the paper tear problem. Start with a single piece of notebook paper. Please get one, and then tear the sheet in half and stack the pieces. Try this. So get a sheet of paper and then tear the sheet in half and stack the pieces, and then tear this stack in half again and stack the pieces. Repeat this process, making sure to stack all the pieces each time. Okay, and then we are going to make a table of the function of the number of pieces of paper in terms of the number of times you have torn the paper. And remember to define your variables. This is very important. You're always asked to define your variables. So x is, you can say that that's the number of tears, and our y is after you tear it, number of pieces of paper. So at the beginning, we started with one paper, and then when you tear it in half, how many pieces of paper do you have? Yes, you have 2. Then when you stack the pieces of paper, and then you tear in half again, how many pieces of paper now do you have? So yes, it's 4. And then you do the same process, stack all the pieces, and then tear in half again. So how many pieces now? So yes, 8. And the next 4. And then how many pieces? Yes, that's correct, 16. So look for the pattern in the table that completes the following sentence. When I increase the input by 1, so this is the input, the x values, 0, 1, 2, 3, 4, what happens to the output? So meaning the y values, so this is your output. 1, 2, 4, 8, 16. Yes, it doubles every time. That is correct. Now the big question is a function from part A linear? And how do you know? Let's start what we know about linear function. So we know that y equals mx plus b, meaning there is a common difference. Let's check our table. When we subtract these two, 2 minus 1 is 1. How about the next two? 4 minus 2 is 2. 8 minus 4 is 4. 4 minus 8 is 8. And as you can see the difference, they're not the same. So that's why this is not linear. So they don't have a common difference. But what do we have here? So actually, based on this, we actually have a common ratio. Like 2 divided by 1 is 2, and 2 divided by 1 is 2, and we are multiplying each time with the same value. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, times 2 is 16. So we are multiplying the same value each time. And because we can see that the y values are increasingly exponentially. So that's why this is not linear. So find an equation for the function in part A. So I just said that it is increasingly exponentially, and that is a common ratio. So you can say that this is y is equal to 2 raised to x. Do you agree? Okay, let's check the values in your table if it matches the equation and show these checks. So let's start with at 0, 2 raised to 0. Any number raised to 0 is equal to 1. So this is correct. And then about 2 raised to 1 is equal to 2. So this is correct. How about 2 raised to 2 is equal to 4. That is correct. 2 cubed, 2 times 2 times 2 is 8. And 2 to the 4th is equal to 16. So this is correct. Now use your equation to determine the number of pieces of paper you would have after the 20th tear. So if we use our equation, y is equal to 2 raised to x, let's use that 2 raised to the 20th. So if you use a calculator, just try 2 raised to the 20th and you will get 1,048,576 pieces of paper. Okay. Next, problem number 2. There are 5 mold spores on a piece of cheese in your refrigerator. Suppose that the spores triple in number every hour. Again, suppose that the spores triple in number every hour. So we're going to make a table showing the mold spore count for the first 5 hours. So that's why you have here 0, 1, 2, 3, 4, and 5. So let's define our variables. So x is the time, that is every hour, and our y is, yes, the mold spore count. So it says here that there are 5 mold spores on a piece of cheese in your refrigerator. So we start at the beginning with 5 mold spores, and then it says it triple in the spores triple in number every hour. So the first hour, if you triple 5, that's going to be 5 times 3 is 15. That's correct. The second hour, if you triple 15, that's going to be 45. That's correct. If you triple 45, that is going to be 45 times 3 is 135. and then you multiply this by 3, 405. Then when you multiply this by 3 is 1215. Okay, it triples every hour. So now what's going to be the equation of the function that models this situation? So this is going to be y equals, since we start at 5, so 5 times, and it triples every hour, so that's going to be 3 raised to x. Okay, so we can check this. Like the first one, y equals 5 times 3 raised to 1. 3 raised to 1 is 3 times 5 is 15. So this is correct. So if you try 5 times 3 cubed, 3 cubed is 27. 5 times 27 is 135. So that is correct. So our equation must be correct. So explain the meaning of the constants in the equation. So as you can see here, we have two constants, the 5 and the 3. So let's define those two constants. So 5, what is 5 here? Yes, that is the number of mold spores at the beginning in your refrigerator. And remember, at every hour the spores triple in number. That's why we have a 3 here. So let's explain the meaning of that 3. So that is, again, the spores triple in number every hour. Okay. Letter D, you can usually detect the mold where there are 1 million spores. Use a table or graph to estimate how long it takes for you to see the mold. Could you have found your estimate without using your calculator? You can try our Desmos. All you have to do is type our equation, y equals 5 times 3 raised to x. If you see our graph here, at the beginning, you have 5, and when you increase this, you will see that, look at the graph, it's not linear. Now the question is, how about 1 million spores? So we can change our y values. So if you want, so here, as you can see, 1 million here, and if I click on this, it's gonna be about, look at your x value here, it's like 11 point something. So after 11 hours, approximately after 11 hours, 11.11, it's gonna be the 1 million. That's the number of mold spores. Okay, so that is by using your graphing calculator or Desmos. Alright, and the last problem here, consider the functions f of x equals 5 times 3/4 x and g of x is equal to 5 times 4/3 raised to x. Which one is increasing and which one is decreasing? You can try to use Desmos and just type this, and you will see if it's increasing or decreasing. So actually, when you type f of x equal to 5 times 3/4 x, it's gonna be decreasing, and g of x is increasing. But why? So let's talk about first our summary here. Exponential functions model quantities that increase or decrease by constant multiple. This is analogous to linear functions, which is model quantities that increase or decrease by a constant addition. The general form of the exponential equation is y equals a times b raised to x. So take note of this. This is very important. Y equals a times b raised to x, whereas the constant a is the y-intercept of the function, and it's often the initial value in context. Like our previous example here, we started at the beginning when it's 0, our a is 5. So that was our initial value. Then the constant b is the growth or decay factor. It is how much the y values get multiplied by for each additional 1x value. So that's why here it triples every time. So that is your b. So here from problem number 2, take a look at your b. Your b here is 3/4, and we said that it is decreasing. So when b is less than 1 and greater than 0, it is decreasing. And look at the b here, it's 4/3. When b is greater than 1, it is increasing. Okay, so take note of that. Alright, so that's it for activity 1, and thank you.